Alright, today everybody we're starting in Chapter 1, Section 1. We're going to be dealing with functions. And inside all functions, you're dealing with the real number system. I want you to pay attention to these rational numbers. What do you notice about all of these rational numbers right there?
They can be put in the form of fractions.
That's right. It's a ratio of two integers. So right here, something I'd like you to add to it. I'd like you to add, say, for example, the number 2, because 2 can actually be written as 2 over 1. So all of these, 0.125, which is actually 1/8, all right, that's a ratio of 1 to 8. That's that decimal. Here's the negative 7/8, 2/3, which is 0.6 repeating, goes on forever. And then we have 2 over 1, so add that. Another irrational number. Notice, irrational numbers are just off by themselves. A very, very, very famous irrational number is the constant known as pi. All right, that's an irrational number. Or any radical that cannot be simplified, like the square root of 7, which here's the square root of 3. These cannot be put in the form of fractions. Integers are just negative and positive numbers, but also I would like you to add in the number 0. So 0 still technically is an integer. It's just either negative, positive, and it does include the number 0. Whole numbers specifically start at 0 and work their way up. Natural numbers start at 1. Think about when you're a kid and you start counting. What do you start at? You start at 1, 1, 2, 3. You know, usually kids don't start at -5, -4, -3, -2, so on and so forth. All right? So these are all of your numbers inside of the real number system. So natural numbers are a part of whole numbers, which are a part of integers, which are a part of rational numbers. You guys see the letters right here? These letters represent these different subsets. So, for example, right here, you see this letter Z? That refers to, it's talking about what? Integers. That's what it's talking about. So this Z right here, in your example, is referring to the set of integers. So we're going to read this. This statement right here, I'm going to write it a little bit bigger. Here we go. This is the set of all x values such that x is less than or equal to 16, but greater than or equal to -3. All of my x values are an element of, this right here, this little e, in your journal, I want you to write the word, this means element. It's an element of the set called integers. So that's all of it in words if you were to describe that. Okay? So this is set builder notation. Right here, this part right in here means x is less than or equal to 16 and it's also greater than or equal to -3. So those are the words that go with it. Now, how would I graph this particular set builder notation? How would I graph this domain? So here's how you would graph it. So what I want you to do, we're going to do a little graph here. We're going to start at -3, and over here on the right, I'm going to put the number 16. 0 will be way over here. We're not going to graph every single number, all right, but you'll get the gist of it. All right, we have -2, -1, 0, a 1, and then we're just going to skip all the way over here. Okay? So this right here, just pretend like it just keeps going, all right, in between. Now, if right here, this letter Z represents just the subset called integers, we are only allowed to plot the points that are technically integers. Okay? So, -3, it's equal to it. That means I can plot that point. -2 is an integer. That is between -3 and 16. So all of these points right here can be plotted all the way up to what? 16. All the way up to 16. Now, you're not used to just plotting sometimes just points. What do you guys remember doing when it was all real numbers? We used to shade things in between. So let me rewrite this real quick. What if I changed the elements? Everything stayed the same. Everything stayed the same except for one thing. I said x is an element of all real numbers. If x is an element of all real numbers right here, then the graph looks a heck of a lot different. What do we still start at? We still start at -3. We still finish at 16. Here you would have that point included. Here you would have this point included. But what am I now allowed to do all the way from -3 all the way to 16? You're allowed to shade every number in between those two. Here we weren't allowed to do this, were we? Why was I not allowed to do that with integers? Because integers don't include what? 0.3, stuff in between, fractions, radicals, okay? Integers are literally just on that number. 1, 2, 3, 4. They're not at 1.4. 1.4 would be a rational number. All real numbers right here, all real numbers include all of those ugly little numbers in between -3 and 16. Don't call them so much okay? Now, we're going to do a little practice right now with how to graph depending on what you have. So here we go. See if you guys can graph this one. Here we go. The set of all x values is such that x is less than 2, but greater than or equal to -3. And all I want you to do is graph elements that are integers. I want you to try to graph that. See if you can come up with a graph that matches this given situation. All right, so here we go. We're going to graph all the x values between 2 and 3, including the -3, but not including the 2. And we're only graphing integers, right? So am I allowed to put a point on -3? Yes or no? Yes, you're right. Put a point right there. Is the value of -2 between -3 and 2? Yes, I can put a point right there. Now, why can I not put a point right here in between? Because I said only graph integers. Okay? What about -1? Can I still plot that? Yep. How about 0?
Sure.
All right, how about 1? Yeah. Okay, how about 2?
Don't you just put an open circle? You don't put it?
You just don't put anything. Wait a second. Why? Wouldn't we put an open circle right there? No, you don't even have to do that. Here's why. Because it's not, that's an integer. Can I plot anything in between the 1 and the 2? No, because none of those are integers. So it just literally, the only integer that I can plot is a 1. That's as far as I can go. I can't go to 2. Yes, sir?
It was the less than or equal to.
Oh, if I put less than or equal to, then I would be able to put a point right there. Okay? All right. So that's how we do graphs, and that's how we do set builder notation. Now, this is the fun part. We get to do what's called interval notation. So write down in your journals, interval notation. Now, what I'm going to do is I'm going to give 2 examples of set builder notation. Okay? So here we go. Here's one example of set builder notation. I'll just use the one that we just did right now. Not that. -3 less than or equal to x less than 2. Oh, better erase this up here. So there's one. And I'll do another one right here. I'm going to say set of all x values such that x is less than or equal to 2, but only greater than or equal to, we'll say, -5. Okay? So let's say we have set builder notation. We wanted to change that into interval notation. Okay? So I'm going to pause it real quick and we'll get started. All right. So all the values between a -3 and a 2, including the 3, but not including the 2. So the cool thing about interval notation is that in interval notation, If it includes the number, you make what's called a hard bracket. So I'm saying this right here means I'm including the -3, but I'm not including the number 2. So since I'm not including the number 2, it's just less than 2, I use what's called a soft bracket. Including, not including. So this right here, this bracket means if you include the number, this number is not included. This is your answer for this set builder notation. You start at 3 and you end at 2, but you don't include the 2. So what if right here, I took that away? Right? So x is now between -5 and 2, but it's not equal to -5. Then I would lead out with a soft bracket. So it goes from -5, the domain goes from -5 all the way to 2, and since it says less than or equal to a 2, I can use the hard bracket. Okay? So what does this expression mean? What inequality does this mean, reading it from left to right? X is what? More than or greater than 2. Does it include the 2? No. So we would put an open circle, and we would shade everything to the right. Now if I do that, I didn't tell you which subset of what subset I was using. So what are you automatically assuming I'm implying that it is? That it's all real numbers. Just so you guys know, whenever I'm doing a problem, if I don't tell you it's integers, the implied domain is all real numbers. If I don't give you the domain, if I don't tell you it's natural numbers, whole numbers, integers, rational, if I don't give it to you, what should you automatically assume? That we're dealing with what? All of them. Okay? So that's what's called that's the vocabulary word right there in chapter 1. If you see the word implied domain, it's referring to all real numbers. This one right here, it says less than or equal to -3. So I'm going to close in that circle right there because I'm including that number. And now I'm going to be shading everywhere to the left, right? Now, Raymond, on this one I'm going to the right. What is this going towards? What concept? We're going, right? That's going towards what? Positive infinity. But this one's going to what? You're right. Negative infinity. Right? So, right here, here's how you would write these in interval notation. We are starting at a 2, but I'm not including the 2. And which direction am I going? I'm going all the way towards. Yeah, so here's how you write it in interval notation. Now, why do I use a soft bracket with infinity? Because you can never actually get to a number called infinity. It's an idea, it's an abstract idea that it goes on forever in a positive direction. Okay? However, right here, it says x is what? Less than or equal to a -3. But it's going towards what? Negative infinity. Well, look. You can never reach negative infinity, but you can get all the way to a -3, right? And that's where it stops. You see how the hard bracket here, what am I saying? I'm saying, now here's the cool thing about interval notation. You put your biggest number on the right, and you put your smallest number or concept on the left. It makes it really, really, really easy. So what's being graphed? Everywhere from negative infinity all the way up to a -3. And what does the hard bracket mean right here? That you're including that number. Let's go ahead right now and see if you guys can do number 1. Look at problem number 1 and see if you can do it in set builder notation and interval notation. So look at problem, zoom in on problem number 1. And I want you guys to look at these numbers and see where it starts and where it's going to and what type of numbers are being graphed. Alright, we're going to start off with set builder notation. I have a -3, a -2, and wow, what type of numbers are these? Integers, yes. We are working specifically with integers. That right there is my domain. Those are my elements. So here we go. We're saying the set of all x values such that all of my values are greater than or equal to a -3. But what are all the elements of x in this particular case? All the elements are integers. You are correct. Oh wait, I'm not allowed to write integers. Oh, if I only knew a letter that represented integers. Z is correct. I is actually an irrational way to represent it. Do you get it? Because I is irrational. All right. There it is. Z represents integers. That's why I want you guys to have your chart in your journal. I don't expect you to memorize them all, but if you have a chart in your journal, then you can use them. All right? That's set builder notation. So I'm going to write the word set next to it to let you guys know that's set builder notation. The next thing I'm going to write is interval to represent the next form I'm doing is called interval notation. So where did we start at? We started at a -3, and it includes the -3, so I use a hard bracket. And that sucker keeps going on forever and ever and ever and ever and ever. So I put plus and boom. Soft bracket because you can never reach positive and it's always a little bit out of reach.
You're infinitely going positive.
Yes. Ooh, we have some boundaries here, everybody. Boundaries on number 2. Boundaries on number 2. Let's do some set builder notation. All right. Set of all x values such. Here's the easy part. X is between 3 greater than -6.5. That part's easy. Huh. What is a -6.5? What type of number is that classified as in our real number system?
Rational.
Rational is correct. What letter is dealing with rational? Q is correct. So I'm going to say x has to be an element of Q, and I'm going to close it at that right there. Set builder notation. All right, so here is the next thing we're going to talk about is interval notation. Go ahead, Raymond. What am I going to do?
You're going to put a soft bracket.
Soft bracket.
-6.5.
-6.5 is correct, sir.
Comma.
Comma. 3.
Hard bracket.
Boom. You're done. It's as easy as that. Okay?